Good morning, good morning, good morning, good morning, good morning. How is everybody doing today? All right, so we are still in Euclid's Elements. I guess that's where we have been and will be for the duration of this course. But we are also still in definitions of Euclid's Elements. So just a little bit of a review before we keep going with new definitions. So we have seen already that a point is that which has no part. It is location without any length, width, or depth. A line is length without width. The extremities of a line are points. And a straight line is one that lies evenly with all the points on itself. Then we know that a surface is that which has length and width only. All right, so we take a line and we add some width to it. Take a line and you take a point and you add length, you get a line. You take a line and you add width, you get a surface. Right? So a surface is that which has length and width only. And the extremities of a surface are lines, just like the extremities of a line are points. We said that a plane surface is a surface which lies evenly with the straight lines on itself. And a plane angle is the inclination to one another of two lines in a plane which meet one another and do not lie in a straight line. Let's go ahead and, apparently I forgot to take off the highlighting from last time, so let's go ahead and just get rid of that. There we go. So a plane angle is the inclination to one another of two lines in a plane which meet one another and do not lie in a straight line. And meanwhile, when those lines are straight lines, then the angle becomes a rectilineal angle. And we said that a perpendicular is a straight line set up on another straight line when the two adjacent angles are equal to each other. When the two angles on either side of that line that's set up on the other one are equal to one another, that makes a right angle. And with the straight line standing on the other one is called the perpendicular. Okay, so let's keep going now. We need a new slide for definition 11. And as a reminder, we're going to go all the way through definition 16 today, just so that we can do all of the definitions in 4 total lessons. So one extra lesson today. Okay, so in definition 16, we are going to define an obtuse angle. This is going to be pretty easy, I think. An obtuse angle. All right, so here we go. An obtuse angle is an angle greater, let's say larger, greater is probably a better word, greater than a right angle. So you're going to see, one of the things I want you to sort of notice here is that the way Euclid does these definitions, you sort of have to have some of the earlier definitions in order to make sense of the later definitions, right? So it wouldn't make any sense to define an obtuse angle as an angle greater than a right angle if we hadn't defined a right angle yet. So you need definition 10 before you can really even think about definition 11. In the same way that it wouldn't have made any sense to say that the extremities of a surface are lines before we had a definition of lines. So, okay, so back to our obtuse angle. So an obtuse angle is an angle greater than a right angle. Let's go ahead and grab our setup from definition 9 here. We're going to drop it into definition 11. All right, there's a lot going on there. So let's first off, let's go ahead and set up a right angle, though. So we know what a right angle looks like. We need a straight line. We need another straight line, and the one straight line needs to be set up on the other straight line. Boom, just like that. It needs to click into place. Now, take my little angles circle here, and I'm going to put my letters off to the side as well. But I think I'm going to use them in a little bit. So I'm just going to put them off to the side for right now, so that we have access to them when we want them. Here, D. Angle D, you can hang out up here. Angle C, we're gonna put you over here with D. Okay. So right now we have right angles. All right, so that's essentially this situation going on back from definition 10. That's the right angles. So right angle A here in this diagram. Angle A is a right angle and angle B is a right angle. But we're looking for an obtuse angle, and an obtuse angle is an angle greater than a right angle. So we're going to make one of these angles greater than a right angle by making it greater. Just bend, still a straight line, but we're going to have it at an, it's not coming straight down now. It's not resting evenly. I'm going to go with Bob and Wanda today. I forgot what their names used to be, but now they're Bob and Wanda. So this is Bob, this is Wanda. Bob is now resting at a slant on Wanda, which means that A, since we just made it bigger, it's greater, is now greater than a right angle, which means that angle A is now an obtuse angle. pretty straightforward, pretty easy to do. And angle B is not an obtuse angle and not a right angle. It is a different kind of angle. In fact, what it is an angle that we will define in definition 11, or in definition 12. So let's go ahead and just jump right into definition 12 and talk about acute angles. That does not mean an angle that is just adorable. Thank you, I'm here all day. An acute angle, so actually, you know what we can do is let's back to our, well, we'll just do the whole thing here, and then I'll make some adjustments. So we're just going to copy our whole setup from 11. Oh, wait, we need to define it first, don't we? Okay, so let's get our definition here properly. An acute angle, agonal angle, is an, oh, get out of italics, is an angle less than a right angle. Excuse me. All right, and there we go. So here we go, and now we're going to copy it again, drop it in here. So going back to our obtuse angle here, angle A. Since we're back in definition 11, I know we're kind of doing 11 and 12 at the same time, but you sort of have to. I hope that's it's sort of clear why you just sort of have to. So let's drop in a word text box and just give our definition here, just really quickly, make it clear that angle. Let's use our little angle symbol here. Angle A is an obtuse, get italics, obtuse angle. That is true. That way you can remember that when you with this diagram. I'm going to copy this as well, and we're just going to drop it in here because angle A is still an obtuse angle, but also it is true that, if I can find my angle button, angle B is an acute angle. And there we go. So in the same way that we had right angles there, angle B and A were the same. And they were equal and everything was beautiful and the same. But then we made angle A bigger, and when we made angle A bigger, we also made angle B smaller because they were the same and they have only the same amount of total space to take up there, sitting on Wanda. So you can't make A bigger without making B smaller. So B is now smaller than a right angle, which makes it an acute angle, and there we have it. And since we didn't actually use angles D or C in this, let's go ahead and get rid of them because they're just hanging out there confusing for when you decide to go back and study this. Get rid of them. All right, there we go. And now it is time to move on to definition 13. 13. We're going to define a boundary. A boundary. Are you ready for this? This is exciting. A boundary. We never really pronounce the A in that second, that A in boundary, do we? We say boundary instead of boundary. It sounds silly if you say boundary. Boundary is, shouldn't be in italics. A boundary is that which is an extremity of anything. This one is, yeah, I'm going to go ahead and grab my illustrations from surfaces. Here. Let's grab some of these things, and we'll bring them down. Here, let's shrink them, though. Shrink. There we go. Move them over here. Let's grab this wonky surface and move that in a little bit closer, because we're going to fit some other stuff. Triangles are fun. But let's make it, well, we'll copy it first. Copy. Just give you some examples of things. And one of my favorite things in all geometricians, what do you think we should call ourselves? Geometers or geometricians? One of our favorite things is the circle. Or in this case, the oval, but we really want the circle. So here we go. There's a circle. Let's go ahead and we're going to fill that one in with red, and let's make our triangle can be yellow. There we go. So the extremity, that means the edge of anything, is a boundary. That's really all we need to know. It's pretty straightforward. One of the easiest definitions out there. So a boundary is that which is an extremity of anything. In this case, all of these extremities are lines, right? The extremities of the square and the triangle are straight lines. The extremities of Waukesha funny thing are straight and curved lines, and the extremity of a circle. A circle only has one extremity. It only has one boundary. Is of course a curved line as well. But as we know, you could also, let's just grab one here. Here's a line for us. Right? If we drop that in here, the extremities of a line, there we go, fit a line there, are points. And, jumping ahead, the extremities of a solid are surfaces, but we haven't gotten to solids yet. There we go. And there it is. All right, let's move on now to definition 14. I think boundary is pretty easy. Definition 14 is a figure. A figure. This is not a person. A figure, according to Euclid, is that which is contained by, not tainted, contained by any boundary or boundaries. Right? How can a figure be contained by only one boundary, you ask? Well, that's where our circle comes in, right? That didn't work the way I wanted it to. Get rid of that slide. Just recopy our circle. Copy that circle. Drop it in here. Here's a circle. It has only one boundary, right? Here's the boundary. You can follow it all the way around. In fact, let's go ahead and make the outline a little bit bigger just to highlight it, all right? There we go. That is a terrible color combination. All right, so there we go. All right, so I have highlighted the boundary of the circle here. And the figure is that which is contained by it. So the circle here, that's the figure is that the part inside the boundaries. Let's do the same thing here with the triangle. We'll go ahead and make our outline. Do that and make it a little bit thicker so you can see it, right? So again, the figure is the triangle that is contained by the boundaries. Now remember that boundaries, in the case of surfaces, boundaries are only lines, so they have no real width. I'm putting width on them just to make it so you can see them easily. But real boundaries have no width, and in fact, if you want to do this really carefully, we can do it, and maybe there's some value in that. So let's do a proper triangle and with proper boundaries. To do that, we're going to need one of these new cool no boundary squares. All right, let's make it a little bit bigger, and I'm going to rotate it because I can do neat things like that. And then I'm going to copy it. I'm going to make a new one. I'm going to change its color. Make it yellow, and I'm going to rotate that one like this. You can see what's happening here. And then I'm going to paste another one in here, and we're going to make that one that weird blue color. We're going to do this with it. All right. Oh, there we go. Ooh, let's shrink it a little bit. There we go. That's the right size. And now let's do one last one. I see some cool PowerPoint magic here. Let's go back to regular. There we go. We're gonna make this one. What color should this one be? Let's make it purple, dark purple. And then what we're gonna do is gonna send it to the back. Send to back. And there we go. There we go. So let's shrink it down to make this really convincing. There we go. All right. And here is a triangle with no boundaries. Well, it has boundaries. Sorry, its boundaries are real lines. That is, they have no width. The line is where the yellow meets the purple, where the, I hope it's purple. It might be dark blue. I'm colorblind, folks, so, you know. Where the green meets the dark blue or purple, and where the light blue meets the dark blue or purple, right? So where they meet, that's the line. It has length, it has no width, and but that which is inside of it is the figure. So the figure here is the triangle. All right, that's a figure. All right, let's move on. We're going to move on now to what are we going to move on to? We're going to move on, here we go, to definition 15. Definition 15 is the definition of a circle, which we've started using without defining, so shame on us, I suppose, but I don't mind. All right, according to Euclid, a circle, and you're going to have to watch this is fun. A circle is a plane figure contained by one line such that all the straight lines falling upon it from one point among those lying within the figure are equal to one another. Okay, that is an interesting thing to say. What on earth is Euclid trying to say? Well, first let's draw what we know as, draw ourselves a circle, right? So we're going to head and, actually we'll just take our red circle here. Let's copy it. Let's drop it in here. Make it a little bit bigger. And, I forgot we can squash. There's a way to tell this thing. I want an actual circle here, people. Circle me. Put it in the middle. I think that's a circle. I think that's a proper circle. Okay. And now let's make sure that it has no outline. All right, there we go. There is a circle. We know this is a circle, but how do we know it's a circle? Well, let's work through the definition quickly. Move this up a little bit more. I just feel like I'm crowded. No, I feel like that's crowded. Okay, we'll call that good. Okay, so a circle is a plane figure. Check. It's a plane figure. Which means it's a figure in a plane. And we know it's in a plane. We can put it in a plane just to make you feel good about that part. Let's go ahead and put it in a plane. Here's our plane. Now the circle's in it. All right, so now it is a plane figure. We'll do it back to our highlighting. Contained by one line. Yep, one line. There's one single line. Such that all the straight lines falling upon it from one point among those lying within the figure are equal to one another. Okay, let's work through this because this is interesting and complicated. Okay. Trying to figure out the best way to do this one. Okay, sorry, that pause there, you saw me pause it when you on the video editing software there. That pause there was because I had to go back and make sure I was going to tell you the right thing. I wanted to do a little bit of research, so I paused and did my research, and now I'm back. So, let me explain what's going on here. Okay, so a circle, plane figure, check. Contained by one line, check, such that all the straight lines lying upon it, and the it here is the straight line, the one line, not the straight line, the one line that is the boundary of the circle. So, the it here is that boundary. So let's just make this really fun, and we can. And so the it is that one line. Right? So from one point among those lying within the figure are equal to another. So what a circle is it's a really interesting plane figure that has a special point in it where you can have all of the lines that go through that point, that touch that point, and touch the edge of the circle, the boundary of the circle. Those lines will all be equal. So let's try this out. Let's get ourselves a line. All right, and we're going to do it this way. We're going to say, hey, look, a line. Oh, I didn't want to do it that way. I want to insert a line. Come here. Shapes, give me a line. Let's make a line here to there. Let's attach this line there. There we go. That way I know it's the right one. Okay, so there's a line, and it goes through the center of the circle. Now what I'm going to do, and you got to watch this. Oops, that's not what I want to do. What I'm going to do, and you have to watch this carefully, is I'm going to copy it, and I'm going to paste it. So there's the same line, and I'm going to then attach it to this one, and I'm going to attach it to this one, and then I'm going to do it again. I'm going to attach it here, and I'm going to attach it here. Boom. And you'll notice that it all goes through the same point right here. We'll do it one more time. Now, since it's the same line, you know it's the same length, and they all go through. Oh, this one got all a little bit off the point. There we go. All right, and they all go through. They all meet in the same point. What that means is that this is a circle. What is interesting about this, from Euclid's perspective, and from a geometer's perspective, is that a circle is the only kind of thing like this. There's nothing else out there besides a circle that has a point in it that you can draw equal lines from to the edge, and those lines will all be equal. So if we label these, and let's go ahead and do a little bit of labeling of these. So I'm going to grab my A here. If we start labeling our lines, here is, right, I'm going to put it up here, line A, and then we're going to add, line B. Oh, I didn't want to do that. That didn't work. Come here, line A. I'll put you there. Line B. Line C. Line D. Line E. We're going to go all the way here, folks. Line F. Line G. And line H. Okay, so you have a point here at the center. We're going to define center in just a second. You have a point, and there is a point, and every line from that point to the boundary is exactly equal. So to put that in, let's put another text box in here and see if I can make this make a little bit more sense to everybody. There we go. I'm going to move my text box over here. If, and let's use our line symbol, oops, not that one. Line A equals line B, which and also equals C, which equals D, which equals F, which equals G, which equals H, then it is a circle. Right? So there's a point, and from that point, all the lines that are drawn, straight lines drawn from that point to the boundary of the figure, and are all equal. And you probably know from class that we call those lines the radius, but you only call them the radius when it's a circle, and we're still trying to figure out whether this is a circle. If this is true, that all of those lines are equal to each other, and they're all straight lines, and they're all meet at the same point, then it's a circle. And in this case, they are, and they do, so it's a circle. Congratulations, and huzzah. And so they are equal to one another. All right, that was a little tricky. But I hope you got that. And again, feel free to ask me questions in the comments section if that one didn't make sense. 15 is one of the harder definitions. All right, 16 though, in contrast to 15, is super easy, and you're going to like it. 16 is the definition of the center of a circle. And all Euclid says is, and the point is called the center. Oops, did not mean to do that. Center of the circle. Circle. All right, there we go. And the point is called the center of the circle. And the point, of course, is this spot right here. So let's go ahead and do this. Grab all that, copy that over, just drop it back in here, because it's getting pretty complicated here. And we missed F. drop F in. Oh, didn't want to do that. Come here, F. There, drop you. Ah, why am I grabbing the whole thing? I don't want to grab the whole thing. I only want to grab F. Come here, F. Try it that way. There we go. And F is there now. So all of these meet at one point. Remember, there is this point from which we can draw equal lines to the outside and to the boundary, and they're all equal lines. So that point, that special point, that one point in this whole figure, that point is called the center. And let's go ahead and insert another little circle. Right, so that's the center right there where they meet. Now, of course, you can't see it now, and the center is a point, so it has no length, width, or breadth. So a point is it's a location, but it doesn't have any actual. It doesn't take up any actual space. No outline on this, and let's send it back. That's not working. Okay, I will just shrink it down even more then. And there we go. All right, so that is the center. Of course, the point is really only in that center. In fact, the point sort of, you can't see it now because it's where all of those lines actually meet. That would be the proper center, but there we go. So today we have covered obtuse angles, acute angles, boundaries, figures, circles, and the center of a circle. Yay! Next class, we are going to move on and deal with, we'll finish up circles. Actually, you know what? I'm going to change things up on the fly here. And we're going to add one more definition because I think we can do it pretty quickly. Now, you know what? I take it back. We're gonna do more definitions next class. So this is going to be it for today. I hope you had a great time. And again, please feel free to leave any questions in the comment section for the assignment.